I think it's okay right now, right?
Yes, the microphone is yours. You can go on, please.
Before I start my talk, let me introduce myself. You already did, but I am Cisem Aktas from Abdullah Gül University in Kayseri. I want to thank the organizers for giving me the opportunity here to talk about my work. So here is my title. I will talk about real structures in real models of K3 surfaces. And this is the agenda for today. First of all, I will start with talking about projective models of K3 surfaces, concentrating on eco-singular strata. Then I will move to a detailed explanation of K3 surfaces, mainly focusing on quartics. Then we will talk about arithmetical reduction, and in the final part, in the conclusion, I will try to explain real models. What's a projective model of a K3 surface? It's in fact a map like this. Here, H belongs to a second homology group, and we call this H as the polarization. And projective models can be studied into two groups, like birational models and the hyperelliptic projective models. We can divide the birational models into three cases like this, where this polarization, square of it is 4. If square of H is 4, then the image of this map inside the projective space of dimension 2 is a quartic surface. If H square is 6, we obtain the image as a sextic, and if H square is 8, the image is an octic surface. When we come to hyperelliptic models, we can look at these two particular cases where H square is 2. In this case, the map is a degree 2 map ramified at a sextic curve, and in the second case where the square is 4, we obtain this map as a 2 map ramified at a curve C like this. Okay, let's talk about eco-singular strata a bit. The eco-singular strata is here, this space, and the M is the space of all projective models that I mentioned in the previous slide. We can collect all such models in this space M, which is a space of all models. And inside here, we have this smaller family, and it is the eco-singular strata with a certain singularity set S, and this can be divided into its connected components that corresponds to eco-singular deformation classes. And I restrict my attention in my work to this family, where I denoted by this sub-index 1. It is the space of all non-spatial quartics. So I reduced my attention to this family. I will explain what non-spatial means soon. And this family lies inside this eco-singular strata space. If we want to look at the general picture again, here it is. The non-spatial quartics are this space, this non-spatial quartics lies inside the eco-singular strata, and this space is inside the space of all simple models, which lies in the biggest space of projective space of dimension n. So this is the general diagram for us. Next, my main contribution is the classification of simple quartics. So I study quartic surfaces with simple singularities. What's a quartic? A quartic is a surface in a projective space of dimension 3 of degree 4. And a quartic is called simple if all of its singular points are simple. I gave a classification of simple quartic surfaces up to eco-singular deformations. And a crucial thing that enables us to study this classification problem was the fact that simple quartics are in fact K3 surfaces. So what are they, and what are special about K3 surfaces then? Here is the definition for a K3 surface. It's a compact, complex, smooth manifold of dimension 2, which is simply connected and whose canonical class is 0. And if you look at the spatial properties of them, these two items summarizes the summarizes what's K3 surface, why they are spatial. So first of all, second homology group is isomorphic to this spatial lattice. So here U is the hyperplane and E8 is the famous root lattice. They are both even unimodular lattices and they have such signatures. And in total, they gave us this spatial lattice, which we denote by L, which is a unique even unimodular lattice of such a signature. And its rank is 22, which is the sum of these two numbers. And second thing that makes K3 surfaces as spatial is the fact that they cannot have singularities other than simple ones. Now, let's look at quartic surfaces as K3 surfaces. So I am working with a quartic surface X, which has singular points. So it is a singular surface. When we blow up its singularity points, we obtain a smooth surface, which we denote by this. And this resulting smooth surface is in fact a K3 surface. So this is our main crucial motivation. And since quartics turns out to be K3 surfaces, we can study them by means of the tools coming with the K3 surfaces. And the most important tools are here, global theory theorem and surjectivity of the period map. These are two strong tools coming with the package of K3 surfaces. I am working with quartic surfaces with simple singularities, so let me talk a bit on them. What are simple singularities? They are of this type, ADE type singularities, and the most important thing about them is the following: they can be identified with the irreducible root lattices. And what is a root lattice then? It is a negative definite lattice generated by the elements of square minus 2. And since we can identify irreducible root lattices with the simple singularities, we will use the same notation for them as the simple singularities. Next, so I used arithmetical reduction to handle my classification problem. So my problem lies on the geometric side. So I have a quartic surface which has singularity points. This is my problem on the geometric side, and I found a way to transform my problem to an arithmetical word. So each singular point here give rise to an irreducible root lattice on the arithmetical side, and these irreducible root lattices lies in this spatial lattice that I mentioned before, which is of this signature. Here I emphasize the number 19 for some reason, we will understand soon. And here S is the singularity set, meaning that on my surface X, I have many singularity points. So this is the sum of all singularity points as a set. And in the arithmetical side, this is the corresponding part. That's why I denote it by the same letter. And this S, the lattice S, is the orthogonal sum of the irreducible lattices coming from each singular point. So this is the correspondence between the geometric problem and the arithmetical problem, and how we did the arithmetical reduction. And here, the minor number of our surface is defined as the rank of this root lattice on the arithmetical side. And since this root lattice is inside this spatial lattice L, its rank should be less than 19, because this is the negative definite part which corresponds to this. So that's why this minor number, which is the same as the rank of S, should be less than or equal to 19. And if it is 19, we call our surfaces as the maximizing surface. Here is more setting to understand how I handle my classification problem. So this is our sublattice on the arithmetical side. Then on this lattice L, we have also this hyperplane section. Then we will consider these two as together like this. And I will be dealing with this lattice now. And Yeah, my surface X is called non-spatial if this embedding is primitive. So now I am restricting my attention to the non-spatial quartic surfaces. Okay, and yeah, this is my problem, classification of non-spatial simple quartics. And on the arithmetical side, I have the corresponding problem. So I reduce my problem to the arithmetical side, which is purely lattice theoretical. And this problem is the same as enumeration of primitive embeddings like this up to isometries of L. And this gives the arithmetical reduction of my problem. So instead of dealing with the classification problem on the geometric side, I will deal with the enumeration of such lattices, such embeddings up to isometries of L in the arithmetical world. So this is the same as the enumeration of all finite index extension like this, where T is the orthogonal complement of this lattice. And here is more details about the strategy of how I did the arithmetical reduction. Yes, we come up to this point. I am interested in the enumerations of all finite index extensions like this. And to enumerate them, first of all, we need to consider the existence of this orthogonal complement. This is what we need to do on the arithmetical side. And this part corresponds on the geometric problem, finding all realizable sets of singularities S. And then once we handle the existence problem, to enumerate them, of course, we need to look at the uniqueness of the orthogonal complement, and the corresponding part on the geometric side means that we find the connected components of the equisingular strata of non-spatial quartics. After we handle the existence and uniqueness part, which corresponding to these two parts on the geometric world, then finally we also look at the existence of real representatives in the real components of this strata. And we contributed two new examples to the literature of real strata without real representatives. So in fact, this page is the summary of the total summary of what we did, what I contributed to the literature. Let's talk a bit on real components. If a component D in our equisingular strata contains a real surface, then for sure it's a real component, but the reverse direction is not always true, meaning that there may be real components without any real surfaces. So this sounds a bit strange, but that in the literature there can be find examples showing that the reverse direction is not true. Up to our work, this was the only example of a real component without any real surfaces. This example is given by Alex Tektiyerev and Ayşegül Akyol in 2015. And what we did, in fact, we developed an algorithm, a general algorithm, which can be applied for all models of all K3 surfaces.
Sorry interrupting you, dear professor, sorry interrupting you. Could you accelerate a little further, please?
Sorry? Yes.
Could you accelerate a little further, please? Your time is running out. Please.
Okay. This is my main result. So it works for all projective models, and we apply this algorithm to quartics and sextics. And in the quartics part, I find two new examples which has real components without any real surfaces. And in the sextics part, this was the already known example, but I gave a simpler proof to this example by applying the algorithm that we obtained. And I thank you. I stop here and thank you for your attention.
Thank you very much for your exceptionally good talk, dear professor. Cisem Aktas from ULAKBİM University of Turkey. Is there any question or remark regarding the talk of the professor. Please prefer question and answer button below. Any? Since no question, then thank you, Professor Cisem Aktas. You can